Okay, so for this next lecture, we're going to look at the action potential. And this may be one of the neatest things in physiology because this process has a role in nearly every system in the body. The means to communicate through action potentials is really what makes us be able to do anything. Move a muscle, allow bone growth, release a hormone, sense that you see a scary cat or whatever you're scared of, peanuts, I don't know, whatever those are. And action potentials play a key role in this. And so what I want to do, I'm going to kind of go through the steps of this more visually, and then we're going to kind of look at what some of your slides show. So we're going to imagine we're in a neuron. All right, so in our neuron here, this is the outside of the neuron. This is the neuron's cell membrane, and this is inside the neuron. So all of this is neuron, okay? Outside the neuron, extracellular fluid, outside. Inside a neuron, intracellular fluid. Now, neurons have what we call a charge. In fact, there's always charges in your body. Think of neurons as having a charge. And so there is a lot of reasons these charges exist. One of the big ones has to do with ions. In fact, normally in normal situations, there is a lot of sodium outside the neuron. Sodium has a positive charge, and there are a lot of proteins inside here. We'll just call them proteins. I know I don't have good handwriting, sorry. Those tend to have a negative charge. There is also a lot of potassium in here as well. And because of this, and especially the proteins, generally inside the cell, we say that there is a negative charge as compared to outside. So we often say that there is a negative charge. There's a negative resting membrane potential. And that's usually somewhere in the ballpark of about negative 70 millivolts. Depends on the mammal, but yeah, we'll just say negative 70. And this is a normal resting neuron until something happens. Spider crawls up your leg, you get scared by the peanut, you feel an itch, you decide, hey, I want to kick the tire, whatever it is you want to do, and you then need to communicate that information down a neuron. And so what occurs is that there's actually channels, proteins in these that control keeping positive charges out and negative charges in. When this occurs, these channels will open, and let's pull up, we'll make these channels red. All right. Their channels here will open, and when they open, there's sodium channels. These sodium channels will allow sodium to come in. And in this area, when the sodium comes in, this area will now become more positive. Okay? And so right here, we're going to make those suddenly positive. And so we say this charge becomes more positive because sodium is coming in. So in this area, we call that depolarization. The neuron is depolarizing just in this area of the neuron. And again, we haven't traveled down this neuron yet. Imagine our muscle is down here. We could draw our muscle. All right, imagine, let's not do that. Let's make it red because muscles should be red. Let's make our red there. So let's make this our muscle, right? It's traveling to our muscles. I don't have big muscles. Oh, there's a big muscle. That kind of looks like a bicep. Woo! Makes me hungry. It looks like steak. So imagine it's going there. Again, we've only depolarized in this area. Well, what happens? When this occurs, when this charge becomes more positive in this area, that is then going to cause other channels to open up. And so let's just draw these other channels here. I probably should pick a different color than red. All right. So these are other sodium channels here. And so when this area becomes more positive, when it depolarizes, it then causes the channels next to it to open up, and sodium comes in there. This area again becomes more positive, causing this next channel to open up there. Again, this area now becomes more positive, which causes this channel to open up here. You get the idea. It's a bad song. It's like a country song, except it's happy at the end. and then it opens up there. And so this area of depolarization, we often call it a wave of depolarization, is going to move down this neuron, ultimately traveling to its end. Now, that's just half of it. And as we can see here, this is an action potential. As we see down in our chart here, we've gone from resting potential. We now have this depolarization right here. But it's only half the story, because we can't have this suddenly more positive charge stay that way. It's got to go back to normal. Well, there are other proteins other channels that allow that to occur. And so there are other channels, and we'll just make them blue, that, you guessed it, kick ions out, specifically potassium, right there. And so after this depolarization occurs, these channels open up and kick potassium out. Because potassium is more positive, it then starts to make this area out here more positive again. And this begins the process of repolarization. And as you guessed it, this occurs down every part of the neuron, the cell membrane. And so right behind depolarization, we have this process of repolarization, where now potassium is entering outside, this area is becoming more positive, and so this charge is returning back to normal. All right, so depolarization immediately followed by repolarization, to the point where we then return back to normal. Now, we actually don't return back to normal. We actually return to too much normal. It's called an overshoot, undershoot, I guess here, but it's an overshoot. There are other proteins in this membrane which are really important. In fact, so important I'm going to draw it over here. They're called sodium potassium pumps. And think of them as they're the pumps that keep all this thing normal. They are the pumps that keep potassium out. Sorry, keep sodium out and keep potassium in. So a good way to think of sodium potassium pumps, they keep sodium out, potassium in. Sodium is salt. It's part of salt. Potassium, what has potassium? Bananas. So here we go. Way to remember it. Salty banana. Salty outside, banana inside. You'll remember that. So these sodium potassium pumps act to keep sodium out and potassium in. And these work great. And this keeps everything normal until depolarization occurs. All right, so this is the process of depolarization. And this is what the entirety here is called an action potential. Now, what makes action potentials unique, it's not just one. It's not like you decide, hey, I'm gonna move my finger. Oh, there was one action potential. No. The way these messages travel is through a number of action potentials. Think of it as like code or Morse code. In Morse code, it's never just a damn. It's a series of signals. Think of sending messages down a nerve as a series of action potentials. The more action potentials there are, the more response you'll get at wherever these messages are going. So if you want to just move your finger, that doesn't take many action potentials. If you want to try to lift a mountain with this finger, I couldn't, but maybe you can. It's going to take a lot of action potentials to send that message, to recruit enough muscle cells to pull that off. So when we talk about action potentials, we're really talking about one, but there's clearly a lot of these that occur in order to get a message, in order to communicate what needs to be communicated. So there's a lot of pictures of this in, where am I here? In your slides. This is a picture we've looked at. This is kind of another graphic of this. One thing I cannot forget, though, is because there is another part to this, and we mentioned this in the last lecture, that it's not simply just about the cell, and that there are cells, there's Schwann cells around neurons. Remember we talked about myelin sheath, and we talked about the nodes of Roland VA. Well, why is this important? Well, here's why. Actually, instead of impulses just traveling down this neuron, instead of this charge just slowly moving down, in real life what happens is that this charge, this action potential, actually jumps from node to node. We call that saltatory conduction. And in myelinated neurons, which is what makes up your motor neurons, this is what allows these messages to travel incredibly, incredibly fast. And so the reality is it's this type of conduction that causes you to be able to snap your fingers quickly, to be able to jump from the spider or get away from the peanut or whatever it is you're scared of with incredible, incredible speed. Okay, so that's saltatory conduction. We're going to talk about synapses in our next lecture, but understand what an action potential is, what its role is, how it's done, and the steps involved in performing it.